Hello, everyone, and welcome to another webinar with the Danish Sound Cluster. Today, we have three really interesting guests to talk about a very interesting topic that is very future-driven. To be more precise, it's the second episode of the Beyond DSP series. Today we have Gary Spittle, who is the founder and CEO of Sonical. Welcome, Gary. We have Adrian Felser, who is the CTO of iDune Audio. Welcome, Adrian. And we have Kulen McCabe, CEO of Segotia. And the topic is, I'll just talk very briefly, but then you guys can get really into it. And it's about a completely new approach to not only DSP, but also to headphones when it comes to the software side. And there's this metaphor of having some kind of an app store for audio for headphones, like audio apps and stuff, but you'll get much more detail from the guys. Gary will go first. He will talk a lot about that. And then Adrian will talk about that, but for a concrete use case example. And then Kulen will also have his own perspective of this. So also very specific example on it. But I'll let you guys get into the details. I just want to say also that there's a Q&A icon there in the bottom. So if anyone has any questions, you can write it there, and then we'll take it at the end. So we'll have all the speakers first and the questions at the end. So whenever you have something, just put it there, and then we'll address it later. And I think that's all for me. So I'll give the stage to Gary, and you can start. Just share your screen and off you go.
Excellent. Well, thank you, Pedro. Thanks for inviting us to this session. I think we've got a lot of very interesting details to go through. So just to start with a little bit of background, I'm Gary Spittle, and I head up Sonical. We've been building ear computers now for the last few years, and we've been enabling people to put very advanced technology into ear-worn devices. But before that, and a bit of history of how we got to Sonical, we were spending probably about 5 years helping headphone companies with new features and new experiences that they wanted to bring to their customers. And as consultants, we were given very privileged access to what they wanted to do. And so we were able to make some observations that won't necessarily have been obvious to many other companies or suppliers into the industry. And what we found is that the more companies that we worked with, we identified a common set of problems, which is that there's a lot of different chips that are available with different capabilities. But every time we started a new project, we basically have to do all the work again. They were not compatible in terms of software and algorithms and frameworks and things like that. And the other thing that we observed is that all of these companies wanted completely different things. It wasn't like there was one killer app that everybody wanted, and if we could just build this app, then we would make everybody happy. It was the exact opposite. Everyone wanted different things, and they wanted different combinations of those things, which made it really hard for us to do all the integration. And some of our projects could easily take more than a year of development time. So we came away from those projects thinking about how can we do things better? What could the industry use that would help them bring these experiences to the end user in a much simpler way? And that's where we came up with this concept of ear computers and defined what Headphone 3 is all about. And that's what I'm going to share with you today. So as you will all know, is that smartphones completely changed the way that we use mobile telephony, in particular, how we use them in terms of apps. So if you think about how we've changed in terms of smartphones, smartwatches, tablets, we can now access any kind of feature that we want after we buy the product. Now, when you think about ear-worn devices, we kind of buy the device and we rely on that manufacturer to tell us exactly what we have to do with it and how we operate it and the features and experiences that we get. But what we really want to do is join up this innovation from the app ecosystem with the endpoint devices. And it turns out it's actually quite hard to do. So we came up with this idea of Headphone 3 so that we could get these apps from the cloud into the endpoint. And to do that, you have to really start with a completely new architecture, both for the product and the software stack that runs on top of it. But that's exactly what we've done. We've enabled people to now build applications and download them straight into their headphones. There's really three main areas of innovation that we've been working on, and it's really about listening. So if you think about headphones, most people think about listening to audio, listening to music, or the sound that's involved with playing a game or watching a movie. And so recreating sound and rendering sound is very important for these devices, but there's still a lot of improvements that we could do. There's been some interest lately around spatial audio, being able to binauralize sounds, monitoring how much sound we're exposed to. All of these things are features that we've been asked to implement for headphone companies. And so there's a lot of improvements that are just in how we use these products with their standard use case. But the second area is about listening to the world. How do we interact with people around us? How do we deal with noise in a more intelligent way, rather than simply trying to cancel everything? Wouldn't it be better if we could cancel some things and maybe hear other things? Being able to have conversations in noisy environments is one of the hot topics at the moment. And how do we deal with the capturing of speech of other people talking and be able to hear that for each individual person? And then the third area, which is by far the most interesting in terms of where we see the industry moving, is listening to your body. So the ear is one of the best locations on the body for capturing biometric data. And we can do some very interesting things with that information. We can look at your vital signs on a continuous basis for remote patient monitoring. We can look at your motion and your fitness levels and your general wellness. It's a great place for looking at brain activity and for monitoring your sleep. Right now, we do some of these activities using a smartwatch, but it's generally accepted that the smartwatch isn't necessarily the best location on the body, and that the data collected there can be slightly unreliable. But the reason we keep using the watch is because that's where the computer is. It's the wearable device that we have best access to, because we can write apps for a smartwatch. So it makes sense that if we could write apps for the ear, we can now unlock a lot better experience for the end user. The other view of the market is to look at what's been happening in terms of the product companies. And I'm sure most of you are aware that the AirPod is the best-selling ear device in the world at the moment. And all of the other companies are really figuring out how do they compete against an AirPod. In fact, how can they do better than AirPods? And again, as consultants, we had access to what these companies are doing, and it's simply fantastic. Some of the features that they've developed are amazing. They're just not able to bring it into the final device because of some of the limitations. And so by creating a computing platform, we can unlock that innovation. We can bring access to these features into the product and let the user decide when they need them. So to see where this fits in with everything else that's going on around the ear, we can start with effectively headphone 1 right at the very beginning. So the first headphones really became popular back in the sort of 1980s with the Sony Walkman. People were wearing these wired devices so they could just squirt sound into their ear, and it enabled us to take music on the go. And it was very popular. And of course, things went digital with the iPod and so on. Then headphone 2 came along where we got rid of the wires. So Bluetooth enabled us to have a wireless connectivity with other devices. And now, because we have a chip inside these products, we can do some signal processing. So we can do things like change the equalization of the music. We can reduce noise on a phone call. We can include echo cancelers and things like that. But Bluetooth itself has actually put some limits around the capabilities of the product. And in some ways, it's trying to define what the product does. which isn't what the product companies really want. They want to have freedom to go and do whatever they want inside these devices, rather than being told what to do by the connectivity standard. So Apple decided they're not going to play this game. They're going to do their own system. They're going to build their own chips, their own software stack, and they can have this custom link between the phone and the AirPod, which means everybody else has really been left behind. And so we defined Headphone 3 to enable these products to move to the next level. And rather than be limited by Bluetooth, let's see what people could do if we built a completely new architecture. So that's where the concept of the ear computer really started. So if you look at the history of processors, you can see why this hasn't already happened. And there's two main components to this. First of all, if you look at the processors that are inside the devices like the phone, our tablets, our laptops, and even like gaming consoles, you see this very strong trend in processor performance. But unfortunately, for most ear-worn products, we've barely gone anywhere. And again, a lot of this is because the Bluetooth standard has kind of identified what the product needs to do and said, you don't need to do anything else. This is what a Bluetooth headphone does. But what we actually want is to increase the compute significantly so we get access to these new features and that are beyond the standard Bluetooth use case. The second thing is the connectivity itself. Again, if you look at things like our mobile phones and our smartphones and our tablets, the connections that we have to networks have also increased significantly. So we can get more data in and out of these devices. And again, Bluetooth has barely changed. So we have to look at alternatives. What we actually need is a lot more data coming in and out of these devices, in particular for some of the AI-based algorithms that are quite large. To get those into a product and be able to adapt to different environments very quickly, we need a bigger pipe. If you then overlay that onto the product transitions that have happened, you notice a very interesting pattern. First of all, these computing devices are getting smaller. We started off with large devices on a desk, and now we're wearing them on our wrist, and eventually we'll have them inside our ears. And what this transition enables us to do through the use of an operating system, we can now have products that are defined by the user. We no longer have to spend a long time trying to figure out and predict what features to put into a device. We simply give the user all the capabilities and we let them decide what they need to do with it because it's different for everybody. And so we do that using an operating system. And we do that by enabling the user to go and get access to apps when they want them and download them at any time. It's no longer a fixed product. And this transition is completely inevitable. We're already seeing this happen with many product companies. The architecture itself, when you take the lid off of an ear computer, it's really no different to other products. There's a main processor that runs the operating system with the application sitting on the top, just like it does in your laptop or your phone. And so when you think about the headphone, we need to get these apps into the platform. We need to have an operating system that works across different processors. So we're not just siloed into one particular type of instruction set or memory architecture. And then we get access to all the other components within the device, such as the radio, the codec, or maybe some co-processors that are an AI accelerator. We get access to those through the main host, and we can write drivers to do that. Once you have this platform, then some very interesting things can happen. First of all, you get access to a lot of different software features. Because we've now made it very easy for people to develop code, and that code can work across multiple different products, multiple different chipsets, we have a common API that allows plugins to be developed. And that was very important when we were observing what developers really want. We've also changed the business model. So not only would we be able to have negotiating licenses directly with the product companies, now the plugin companies can generate revenue by going direct to an end user and actually have apps that they could be purchased through an app store. So the end user then gets all of these benefits. They have access to hundreds of different features. They can download which ones they need. They can change their mind at any time. They can try before they buy. So now the dynamics of the system are a lot more fluid. And the product companies also benefit because now they don't have to try and predict and do all the integration on one particular chip and then find that all of that code is completely incompatible if they wanted to change to a different processor in the future. Now they've got the freedom of hardware and software choice. Some of the features that we've already identified and enabled with our first products that will be launching next year include things like very high data rate audio streaming for audio files and for professional use cases such as in recording studios. Being able to have multiple channels of low latency audio for things like gaming and watching movies. Now that can happen because we're no longer tied to just a Bluetooth connection. We can offload large amounts of processing if we need to. So when latency isn't so important, we can take very large AI-based algorithms and run them on a coprocessor only when it's needed. So that kind of interaction is something that the OS allows. But one of the key things that we had to build was what we call eardrop, the ability to take applications and just drop them into your earbuds whenever you need them. So how does the system actually work? So normally this is the point when we would do a live demo. I'm not going to risk that on this session, but instead this animation kind of explains just how the system puts everything together. So in the same way that you use your phone to access apps today or your tablet, you will have applications available to you from an app store and you will download them to your tablet. And then inside each one of those apps is what we call a plugin. It's the signal processing code or the algorithm that is used for that application. And what we have on the ear device is effectively an ear computer. It's a processor or a set of processors that's running an operating system. And what we do is we take the combination of plugins that the user wants, we send them over a wireless link, we embed them into the product, and then we activate them. And all of this is done completely seamlessly. It can be done while I'm using the device. It's not an over-the-air upgrade or a firmware change. All of this is done seamlessly at runtime. So just to summarize, the way that we see the future of ear devices moving is towards this ear computer platform, which is really the foundation of Headphone 3. We want people to escape the limitations of Headphone 2 products, where it's just a Bluetooth link for playing music or making phone calls. We want to enable a huge number of new experiences. And to do that, we of course need apps. We need to work with developers that can generate these amazing features and get them into the product very, very quickly. The products themselves will have access to more sensors. So we won't just be playing sound or capturing sound. We will actually be measuring the impact on the body, because if you can measure what something is doing, then you can improve on it. You can do something about it. So we're seeing companies add more and more sensors into their devices so they can look at things like your heart rate, so that when I'm listening to music, I know for certain that this music is helping me relax or it's helping me get excited. So we have a very personalized interaction between the sound and the body. We know we're going to need more connectivity. So we're already integrating other radios into the products. We've built drivers to talk to UWB and Wi-Fi so we can extend beyond Bluetooth. And all of this is presented as a system so that each individual company doesn't have to go and do that work again. It's the same model as laptops and phones where we have drivers to do that function. And then this will, of course, enable the devices to be used for more activities and use cases during a typical day. It won't just be something that we use for work, for Zoom calls, or for listening to music. We can now use it for other parts of our day as well. The final piece is about the extension into other devices. So a lot of the companies that we're already working with, they also build other products. They don't just build headphones and hearables. And so the operating system and the concept of this embedded computing platform that can run applications is something that's already being put into other systems. So we have products that will be launching using our technology for speakers, microphones, and some other wearable technology like fitness bands and health monitoring. So the concept of being able to put apps into these things has already been extended. And that could be an extension for some of the algorithm developers who may not be simply about audio. They could extend it to other products as well. Okay, so the session really has been to introduce you to ear computers and how we can help develop new products based on this architecture. We will have the first headphones launching next year that uses this concept, this whole technology stack. We already have quite a few plugins that are ready to go, and those companies are already working with the product developers and also with end users to establish that ecosystem of apps. We'd be very happy to bring on some more companies to join this journey with us. Thank you.
Thanks, Gary. That's great. All right. We don't have time for questions right now, so we'll just jump to Adrian. Just gonna. So feel free to start whenever you like, Adrian.
Good. Yeah, my name is Adrian, and I work for a company called iDoon Audio. We develop and sell a spatial audio algorithm that uses first principle physics modeling to do spatial audio. So we rely on things like an IMU, an inertial measurement unit that fits onto the actual headphone or earphone to measure a user's or listener's head orientation. And then we model, sound spatially as it would occur in a real listening environment. Now, I want to take a bit of a philosophical step back first before I get into anything technical, because I think we're on the cusp of something really big here, and something that's actually haunted me for quite a bit longer than, quite a while before I even met Gary. And to kind of appreciate that train of thought, I just want to get you all to join me on a bit of a thought experiment. So just bear with me, it will be quick. So first of all, imagine transporting yourself 600 years into the past. And at this point in time, all writing that happens gets done by hand in monasteries by monks, mostly on a very singular topic and in Latin. So general people don't read. It's just not something, you can buy a book if you are extremely wealthy and then have this book as a kind of artifact, but it's not a conveyor of information. Now let's ask ourselves, as this person 600 years ago, how will we think in future? And what happens when we have other people's thoughts right in front of us? I don't think any of us can imagine anyone being able to extrapolate all the second, third, fourth order effects that come out of this single question. So let's jump ahead to 150 years ago, just before the invention of the telephone, and ask ourselves, how will we talk in future? And what happens when you can speak to people far away as if they're right in front of us? Do you think it's imaginable that anyone could extrapolate from that the birth of something like the internet? Or no, I don't think so. The point I'm trying to make is, let's jump to the next one. I mean, computing. How will we do everything in future? I mean, there's no way you can, by looking at a new invention or new technology, successful new technology, extrapolate what will it do in future. And it's always massive. I mean, the thing here is the first order effects of a change is small. The really big changes are in the long tail and in the second and third and fourth order effects. And this is where I now want to, this is basically the question I want to get to. And that is, how will we listen in future? And I think this is big. It's much bigger than we realize. What happens when we have computers in our ears? We've not seen the beginning of this yet. I'm pretty sure of that. So this question, or my obsession with this question, started a bit more than 10 years ago, when we were in Copenhagen visiting my brother-in-law and his family for Christmas. And in that quiet time between Christmas and New Year, he took us for a tour of the company he was working at the time, which was Oticon, just outside of Copenhagen. They a very large hearing aid manufacturer. And something in my head just, I think, snapped during this tour, where previously I've thought of hearing aids as essentially amplifiers. And I suddenly realized that these are not amplifiers. They are computing platforms, and they're pretty efficient, pretty powerful computing platforms. And I mean, I couldn't get, my mind just started racing for the rest of this holiday period. And I went home with this whole idea of, this is going to become a consumer device. I just can't see a future in which this doesn't happen. I mean, it brings great benefit to people with hearing disabilities, making life a bit more normal for them. And I don't want to detract from that function and that benefit at all. But there's so much more that this device can offer. And I started sort of digging a bit further, a bit deeper and deeper, and then realized at some point that the reason why this is such a compelling kind of device is it's all about information. If you think about how much of the information that you store in your head enters via your ears, then you kind of start getting a glimpse of, why is this super, super powerful? And it's a completely untapped sort of almost sector of humanity that's not served by technology yet. And this is where I then sort of went on a thought experiment and thought, so what would be the killer app for this device? And came up with this thing that I eventually ended up calling it artificial memory, something like that. But it's just a one use case. But imagine you have these computers in your ears that listen to everything you hear, store it and index it, so that you can ask questions like, when I went with drinks or for drinks with Neil last week, he talked about an amazing movie. What was the name of that movie? Or 2 years ago when we were in Italy, we stumbled on this village in the mountains and had lunch there. And what was the name of that village again? You know, just things you can ask an indexed database that has access to everything that you heard in the past. And now, I mean, that is a completely naive use case, because think if you combine that with like proper modern day AI, like GPT-3, for instance, what could come out of that? So I really think this is big. Then in 2016, this happened, and I thought, okay, this is it. You know, someone else also had this idea. They've worked long on it now, and this is going to happen now. And I immediately saw the future of AirPods. I thought, okay, it's going to launch like as a tethered, you know, basically just earphones, Bluetooth earphones. But they are already, it's an independent computer in each ear. So I saw this gradual decoupling strategy, and I really expected Apple to do that. I thought, okay, the next version is going to be, you know, slightly more decoupled, and over time, it's just going to become this entirely independent device that can use the phone in your pocket as a kind of local cloud, you know, for processing power, but most of the time it's an independent device. So I'm very often wrong, and this was one of the cases. Like, it's not the direction it took, right? They went completely the opposite direction, where today, if you want a full feature set out of a set of AirPods, AirPod Pros or AirPod Maxes, it needs to be coupled to an iPhone, not even any phone. They did introduce the world to something interesting though, and that's spatial audio, which obviously is interesting to us. So that's exactly what we do. And that's around the same time that they launched spatial audio. I also, completely unrelated, but I also joined same brother-in-law who took me for the tour of Oticon, his company called Aiden Audio. And we sort of kept working on this spatial audio algorithm, which our algorithm is very much focused on running the algorithm on the earphone or headphone hardware itself, so as to not create this sort of walled garden effect of, you know, you might know Apple's spatial audio has to run on the iPhone, and that's why, you know, you can only experience it if you use an iPhone. Now, that's when our whole go-to-market strategy exposed me to something very interesting. Like, I think the bit that I found surprising is which part of all of this is hard work. And our strategy basically, it has us speaking to headphone manufacturers, get them to buy into the idea of having spatial audio in their products. And since Apple's launched it, you know, that's made that part of the job quite easy. And then we have to find out what hardware they run, which chipsets, and then speak to those chipset manufacturers. And then the penny really drops when we ask the question, so where are we going to get inertial orientation, head orientation data from? Because that's the point where we realize, okay, we're the first consumer or the first vendor on this platform that requires orientation data from an IMU. And that, the porting of the software, I mean, our dependency chain is essentially zero. So we usually get the software compiled and running within a few hours. And then there's a bit of an optimization cycle where we figure out, okay, this platform that we're dealing with, or this chipset that we're dealing with now, what kind of custom code processors or hardware do they have? And is there anything that we can leverage to make our code run faster? But the bit that's proven to be the hardest is this idea of introducing a new sensor. It sounds simple, like, you know, just add an inertial measurement unit. But it just has all these sort of, there's first the whole bill of materials issue. And I mean, there's a physical device that now has to be incorporated into the design that wasn't there before. But the second part of that is, you know, this thing has a driver has to be written for this inertial measurement unit. And on each of these devices, you know, or these chipsets, you have to implement it in a slightly different way. And then we met a headphone manufacturer. Well, we initially saw them as a headphone manufacturer, but very quickly, you know, they revealed it, or we saw that they actually something completely different, and they have a completely different approach. I mean, I'm not going to repeat what Gary has already said, but from a developer point of view, it's really interesting that, you know, Sonical brings this audio-oriented operating system with proper hardware abstraction, and you build on top of APIs, you expose APIs yourself. Everything kind of fits into this very sort of structured, almost a really open standards-based approach, which enables collaboration. So yes, we still, I mean, being the first software in the ecosystem that required an IMU, we still had to write a driver for our IMU. But we could write that driver in a very well-defined driver framework. And that driver becomes available to anyone else who might need an IMU. I mean, in that ecosystem, we could even possibly try and monetize that driver if we wanted to. And that is quite, I mean, if I just give you a bit of an overview of what this framework architecture looks like. I mean, you have the UI, which then sits above an application. And this is the powerful bit, where this application then determines a graph of plugins, or configures a graph of plugins. And these plugins can really be written by different vendors. This is where this idea of creating an application becomes a much more lightweight concept, because it builds on work that others have done in the past. And I think this is a really, really powerful concept. But if we think about it, I cannot resist just saying that, you know, this actually looks quite familiar. Like if you take this whole thing of walled garden versus open standards, it feels like the whole thing that we've seen play out of proprietary versus open source. I mean, I started off when I made this slide by putting down Microsoft and Linux, but I thought that was maybe a bit provocative. But I mean, I've said it. It's kind of that approach, and I'm not saying one approach is wrong and one approach is right. I just think the approach that enables the future of, or that has the biggest effect on the future of humanity, is always the approach that enables these second, third, and fourth order effects. And that is where open standards and open source kind of approaches, in the long run, it has by far the biggest impact on humanity. And it's kind of this thing of, you know, are you building a company or are you building an industry? And that is, in short, why I think this is really big. I mean, putting computers in our ears is an amazing thing. We can, I really think we're moving towards a future where hearables, or, you know, things that we wear in our ears will maintain their own connections, have their own connections, and they will have their own interfaces. You know, where you can kind of decouple yourself from this small screen that we carry in our pockets all the time. And that's why I'm excited about this, to be honest. Thank you. That's it from me.
Thank you, Adrian. That's very good. Very reflective. I like that. Let's just remove the spotlight. So Kulen, whenever you want to share, you're very welcome. We have quite a bit of time, so no stress.
Sure. Thank you, Pedro. And thank you, Gary, and thank you, Adrian. So I'm Colin McCabe. I'm a founder and currently CEO of Segotia, which is an audio DSP company that, as well as, if you like, the traditional types of work with which you might be familiar, we are taking a bet on a next generation of hearables, specifically in relation to neuroscience and neurotech. So the presentation that I will give today, if you like, is our very specific view of the opportunities that we see that arise when you have the likes of Cosmos in devices in people's ears. The fact that this is an operating system that runs in an ear allows us to connect some pretty interesting dots to produce some pretty incredible user experiences. Or at least that's the narrative that we are exploring. and the future so far looks real bright. So let me just tell you a little bit about where we come from. So we're a traditional audio company. We've been doing, if you like, traditional audio for 5+ years. Initially formed by myself to bring my experience in spatial audio and acoustics to bear on hearables. I did a PhD in surround sound psychoacoustics over 25 years ago. Interestingly, the day I got my PhD, there was no device that could run the result. Fast forward 25 years later, and now everybody's about spatial. So we formed Segotia to, if you like, capture some of that and consolidate some of our experiences. And yeah, it's a great company that does some great work with some very interesting companies and products and devices and so on. But we too had a beyond DSP moment. A little over a year ago, we asked ourselves, what's over the horizon? What can we do beyond just the traditional DSP that would allow us to partake in a future of audio? So we opened up our books and went back to the research papers and talked to our friends and confidants and advisors, and we discovered neurotech. And we were quite lucky in a sense. Our heritage associated with Trinity College in Dublin allowed us to meet and talk to Edmund Lawler, who was a seminal part of the discovery of a neurological cognitive process called auditory attention decoding, about which we'll talk a little bit later. It was one of those oh my God moments where we realized if we could get some markers from this whole neuroscience thing, we could really see the relevance to audio experiences, and we could join the dots into getting them into consumer devices, because this is what we do every day anyway. So this was, if you like, our beyond DSP moment. So we hired a neuroscientist straight out of Google Labs, and Mick Cross and our super rock star audio engineer Ian Davis got to work to see how can we join these dots and what sort of experiences can we do. One of the first things that we realized, well, how are we going to get this here EEG? Because we sure as hell aren't going to be putting on these here swim caps. So our next step became almost inevitable, although we didn't plan it. We said, well, let's just look at exactly what we need to capture here. Where is and what is EEG? So I won't go into a science lecture here on EEG, but in short, they're brainwaves. And brainwaves, if you like, encode some very complex cognitive processes and processing. And you may very well have heard of alpha and beta and theta signals. EEG encodes a whole lot of very, very complex stuff if you know how to extract it. That's the hard piece. But again, how are we going to get at these EEG signals in a product that's going to be realistic as a consumer form factor? Again, it sure as hell isn't going to be a swim cap. So we decided, well, you know what? Let's just make an earbud. So working with a partner, we got Ian to fill his ears with wax. We made a 3D model, and working with that partner, we designed this solution right here. It's a pretty complex piece of gear. As you can see, we have, as well as the 3D printed sort of shape that fits the personal ear mold, we also had to design some pretty complicated tubing to carry the electrical signals free from each other's interference out to the outside world. But we made the thing, and it works brilliantly, and it's a fantastic fit for one person on the planet. And that's fine. It allows us to proceed and do some great science with this rather excellent piece of gear. Here's what it looks like. So this is our custom molded EEG enabled earbud. It's a world first. We've got 8 EEG sensors in there. We've already tested them. We see EEG signals. We're pretty sure they're high quality. We have 8 channels from each ear, which is quite a lot compared to the scientific understanding that we have in terms of how many we're going to need to do the types of decoding that we want to do. But it's a hell of a start. And now we get into the science of crunching the numbers we get off these 8 sensors to try to figure out how many we need, where the optimum positions should be, because ultimately, one problem about this earbud is it doesn't play audio. It's just a piece of plastic with some sensors. So we're pretty sure that other companies will solve this problem. How do you fit in an SoC? How do you fit in the driver? How do you fit in the electronics? What about if you want to go TWS? We have 2 independent electrical entities. What sort of engineering problems does that give rise to? So suffice to say, there's a lot of work to be done, but now we have a scientific tool with which we can proceed and figure out some of this science piece and come back to the hardware with a partner later. So about the science piece, simply put, we want to close the loop between the stimulus that we create to a user and the feedback that we get via their EEG. So the stimulus could mean whatever it may mean, depending on the app or the experience. It could be audio, it could be real world. The point is we have now a feedback loop where we can capture EEG, and we have science that crunches those EEG data to produce mental states. We call them neuromarkers in general. These are markers of mental states or mental activities, cognitive activities, and so on. And there's a whole bunch of them that you can decode from EEG if you've got the science and the knowledge to do so. The one that we're most particularly interested in, again, it's auditory attention decoding. And this is the proposition that by looking at EEG, one can tell what efforts the person is making to attend to a specific subcomponent of the entire sound space that's been presented to them. For example, a talker in a crowded environment. So let's jump into that. It's called the cocktail party effect. You walk into a cocktail party, there's 50, 100 people talking, and you can't hear a thing until you stop and think and zone in on somebody, probably by looking at them, probably by tilting your head, but you can zoom in and execute a kind of an audio zoom through brain work. It's called auditory attention decoding, and it is super interesting when you actually see it in real life. Humans do it. We said about understanding how it actually works. And we drew on our scientific backgrounds, knowledges, advisors, data, and so on. It's highly complicated, but I will try to simplify it here in terms of what auditory attention decoding actually looks like, so to speak. So you have a user. In this case, our user is wearing the head cap, but it could just easily be wearing the Scotia earbud or another similar product. We capture EEG while this user is listening to a multiplicity of sound sources and trying to zone in on one of them. In the EEG, if you decode certain features out of it using pre-trained models, you can reconstruct, if you like, the volume envelope of the sound that this person is trying to extract out of the babble that they hear. And you can almost visually match the reconstructed envelope that we reconstruct from the EEG to the actual envelope of the audio, as you might see in a waveform diagram. It's as simple as that. Of course, it's not really that simple at all, because in the scientific tests, there are lots of controlled conditions like isolated speakers, a priori knowledge of the speaker, timbres, and so on. Whereas in the real world, you walk into a room, there's 100 people talking, you've never been there before, there are a lot of unknowns. Well, luckily we've got audio expertise that can insert front ends before this kind of a system that will source separate in advance and perhaps taking feedback from the AAD decoder, pre-clean and pre-separate audio sources into multiple streams and make the job of finding the one we're after in EEG terms a lot easier. So it's extremely exciting stuff, and it promises a lot in terms of the Scotia proposition, if you like, of marrying audio expertise and code with our emerging innovations in neuroscience and neurotechnology. So we wrote some infrastructure for ourselves. in order that we could manage our own IP and run science in the cloud and hook up signal chains and do stuff like that. And this was very useful for us because, of course, it was the beginning of what we now call the Segotia Marketplace, which is a marketplace where vendors put DSP IP and describe these IP in terms of their capabilities, their benchmarks, their requirements, and so on, in order that those pieces of IP could be, for example, sold as IP or bundled with other IPs, but generally speaking, to be, if you like, atomically branded as an IP plugin product that's available via an API to anybody who needs to pop that in. So you'll see where this is going for us. This is the Sonical market. This is a market where you can switch on your companion phone, interrogate the market, find, for example, the Segotia superhuman hearing AAD-based assistive hearing plugin, and download it to your device and run it, right there. So we're very happy to be working with Sonical on that, conceptually and on the back end and in terms of APIs. And of course, we'll be interested in placing IP in that marketplace as well as facilitating others. But other interesting things happen when you participate in a communal marketplace. And when we've seen it before, when you open things up, people start to innovate. And this is what we look forward to seeing. A democratized IP creation ecosystem, a system that allows the end user, the consumer, to design their own product by daisy chaining one or more available IPs. I don't see why I don't have my headphone perform in one way for my jog in the evening and then switch and provide me different features when I sit down to relax on my sofa. So to break the one piece of plastic, one function model is key to this. And of course, it's exactly the sort of things that we're talking about today. In terms of our specific interests and the marriage of neurotech and audio for next generation user applications, there is an interesting thing when we start to talk to vendors about what they're offering on such markets. And indeed, one of the things that occurred when we compared notes for this, when we talked to Adrian, for example, of IDEN, we sort of realized, wow, well, that's an interesting thing. If, for example, in a future product that had a Segotia AAD assistive hearing solution running, well, if we knew that there was a head tracker on that device that was active at that time, then we could definitely use that data. We could simply query the head tracker's API, get the current quaternion, convert it to what we need, so that we can say, hey, the guy is tilting left, the guy is tilting right, he must be trying to zoom in on that over there. And that's, for example, is some intelligence for us to be able to improve our AAD UX. So we see an interesting opportunity for vendors DSP IP vendors to discover each other and create bundles of functionality, which ultimately is going to benefit the consumer, and that's what we all want. That's it, guys. Thanks for your attention. Yeah, looking forward to seeing where all this goes.
Thanks, Cullen. Very good. So I'm going to just remove the spotlight from you, and then we can start our questions and answers. There's not a lot so far, but we'll try to make this entertaining. I have a lot of questions again, because I'm completely neutral, so I can come up with a lot of questions. But first of all, we have a question here from Adrian for you, Cullen, which is, how does the fidelity of the EEG differ between skullcap and earbud?
Firstly, I mean, skullcaps give you about typically 128 channels of data. So purely from a gross numerical point of view, 128 is better than 16, one would think. But let me put it this way. To put on one of those skull caps, you have to cover your head in this ugly gel and then go take a shower afterwards. So it's absolutely, completely not a comparison that one can make in any real world view of the future. But it's a fair question. But happy coincidence. If you can stick something into the ear, you get really good electrical contact. And another happy coincidence, you're getting closer, geographically speaking, to the audio cortex and where all the good action is. Happy coincidence. So I guess the answer is, Adrian, I'd have to defer you to our neuroscience expert, with whom we'd certainly introduce you after the show, to sort of drill into the details. But it's a key question that we need to answer yet, because we're pretty sure that we can't even have the luxury of 8 sensors in an earbud. We simply won't have room for that. But the question becomes, okay, is 2 enough? Is 3 enough? Is 4 enough? And if so, where should we put them? Because we can make very, very good choices there, and to improve electrical considerations, mechanical considerations, and data considerations. So I hope that's a useful answer to your question, Adrian.
Excellent. Thanks.
Can you tell us why it's better in the ear? Is it because of the pressure, or is it because it's closer to the brain, or is it because the skin is less dense, or what is it? It's a lot simpler. You're touching skin with not much hair. Okay.
And there are other factors. You happen also to be closer to the areas of interest in terms of auditory phenomena. Yeah, right. But right. You're making good close skin contact right. with consistent pressure. And also, you're not susceptible to the sort of movement artifacts that you could get with an over-ear physical device. So a couple of nice happy coincidences there that make right. for good EEG capture potential in an in-ear form. So probably the fit is also a contributing factor. Like if you're repeating the stimulus, you want it to be as stable as possible. Or... Sure, and you want it to also be, in highly similar positions every time you put it in the next time, so that right. you get to repeatability. Right. There's a challenge for, I think, all companies, not just neurotech companies or audio companies, to make a one-size-fits-all earbud, right? And it becomes a lot more acute when you require good skin contact for a good EEG sensor. But that is a very, very, very valuable problem to solve. Right. What about the distance between sensors? Does that matter to get a good measurement? I have to say, Pedro, this is where I, stop pretending to be a neuroscientist. Okay. So okay. I'm sure the answer is, of course, there is, okay. a good scientific rationale for the right decisions. Right. I'm not privy to that information right now. Cool. Great, guys. Do you have any questions to each other that you wanna ask? I have a few questions here. I see a very interesting question from Andrew Bellavia there, which is actually something I opted not to touch on in the slides because it's quite complicated. But seeing as it's raised, TWS presents a particular problem. Because, of course, when you're dealing with sensors, and in particular EEG sensors with extremely small voltages, then it's very important to have a solid ground, a solid reference. Like, what does 0 volts actually look like, and where do I get it? And that's fine. In fact, on a skull cap or indeed an eye device, you can simply nominate one to be a reference, and then you measure everything else against that, and at least that's self-consistent, and that's fine for one ear. Because in a TWS solution, now you've got another physical device, and it is, electrically speaking, completely floating relative to the other, notwithstanding the fact that they're touching the same head. So we have some work to do, and I think there's some very interesting innovation possibility in terms of being able to reconcile the fact that we have 2 TWS physical devices that are, if you like, their own atomic separate entities, how to be able to look at the EEG data that comes off them both independently and somehow reference those to some common. And that's a question of not just electrics, but data and trends. So just some interesting science forthcoming on that, I think.
Great. I think we have another question here, but I think it's for Gary, right? Gary, what is the connection data rate that you envisage, and how will this balance power consumption in a wearable device?
Well, I guess the obvious answer is just more. Everyone we speak to, they always want more. They want more data in and more data out. They want it to be running for more periods of time. And obviously that's going to have a pretty significant impact on how long your battery lasts. So, if you think about the product as an entire system, the battery and the power for the radio is obviously one significant chunk, but you've also got the processing. You've got to be able to create audio and amplify sound. You've got to talk to multiple sensors. So as a system, we're going to be using more power than a basic device, for no question. And many companies are already focusing on how to get that power down. But once we've done that, it creates its own momentum. So in the same way that the original smartphones, the battery didn't last very long, and the more you used it, the quicker the battery drained. People are used to that concept. They understand that if I use the device for more things, my battery's not going to last very long and I have to keep charging it. But that encourages the innovation to improve batteries and to create more efficient sensors, more efficient radios. But in terms of the actual data rate, the applications that we're working on right now require at least a 10x improvement over Bluetooth. That's not just for streaming audio information, but also getting applications into the product while it's being used. We don't want to have to turn the device off and put it into its charging case just so I can download a new app. It has to be seamless. Otherwise, it's a bad user experience. So we need that extra bandwidth so that we can submit these other applications. And the applications are getting bigger. So it's not just a case of sending, a few EQ coefficients. We're sending entire neural network models over the air and getting those into the chip and then activating them on the fly, and then being able to update them with new coefficients. So the bandwidth has to increase, but that enables the new features, and that will encourage the manufacturers of those components to make a more efficient system. So we're already at the beginning of that journey, but it's not going to be solved in one iteration. It'll be a continuous process.
Great. Thanks, Gary. We have another question here from Begdad Ayad for Gary. How do you see the hardware the headphone 3.0 in a multi-listening and or playing back audio devices environments, such as a second is this headphone or HD? I don't know, HD 3.0 or a car or a meeting room, or etc. Not sure I understand. How do you see the HD 3.0 in a multi-listening and or playing back audio devices environments, such as a second HD 3.0 or a car or a meeting room? Do you understand that?
Yeah, I think I get the gist of it. Okay. So again, the system would enable multiple users to experience a single source or even independent variations of that source. So imagine if it's a family at home watching a movie, then what we actually want is personalized sound. We don't want everything to be done at the source. And then, if one person turns their head with the head tracker, now everyone experiences that, because you're going to get people, vomiting because somebody's shaking their head and everyone else's spatial scene is changing. So you have to do a lot of these things locally. You can deliver the same content, but you need a personal render of that. Similarly, for things like conferencing, sometimes you could be in a room, but the speaker in the middle of the room isn't necessarily producing the right kind of sound for every participant. So I need a personal representation of that sound. Maybe I have a slight hearing loss and I need a boost, or I'm sitting further away and I can't quite hear what's being said. So being able to personalize that sound independently and discreetly, wearing a device that doesn't make me stand out in the room is something that a lot of people are currently working on. You can then take that to more independent multi-person use cases like call centers, which can be very noisy environments and very stressful. But if we can do things like more intelligent noise control and understanding speech better and monitoring the impact of that environment on the person, such as EEG data and other sensor data, then we can do things about it.
Cool. All right, I think that's answered. All right, I have a few questions. Well, there's nothing else, unless I missed something. Let me know if I did. So one of my biggest curiosities as a hardware developer is as a developer, what is the experience of that Sonical is creating for a developer, as opposed to the current solutions that are, like you guys are saying, walled gardens, they're very closed, and you have to learn it for one product, and then if you change chips, you have to learn something completely new for the next product. So that's not a very good development experience. But so how are you improving in that sense that could change things not only for the user, but also for the developers?
Well, I'll go first on that, and then I'll let the other guys share their experiences. But the intent here is to effectively be like an Android development system, where you can create an app for Android and you know it's going to work on every phone, TV, car infotainment, tablet, smartwatch. You build your app without knowing anything about the chips that are inside those products. And so by having that separation and enabling the freedom for the manufacturers to then put whatever chips they like into their product and differentiate on capabilities, but knowing that there's a whole ecosystem of apps that can run on it, that's really important. So the developers get access to a lot more target products in the market. They can do it much faster because they don't have to understand all the intimate details of the chips. There are some great chips that are available in the market today, but they're very complicated in terms of their architecture. And what we find is that developers have to understand all the details of that chip, the memory system, the pipelining, which cores have they used. And there's been a trend recently to put multiple different cores into processors, but that creates a nightmare for the software guys because now they need 4 different tool chains. They need 3 different debuggers, and these things are all running simultaneously. So it looks great as a data sheet, but it's really hard to actually use it. So we're trying to create this common API that allows the plugins to run and remove that headache from the developer.
Okay, but if we pick up that example, and I'm not an Android expert in any way, but I think that most Androids run on the same chips, right? Like Snapdragon something. So they all somehow are, this is still a monopolized architecture somehow, even though it's a more open, because you have different brands doing Android, but the chip inside is still the same, or am I wrong? And would that be the case for this example as well, or would you really think that you could make something that is compatible with several different chips?
No, it already works on multiple chips. So
okay.
The whole system works on chips that use ARM cores. It could be a hi-fi DSP core. It could be a RISC-V core. The whole point is we don't insist on it only working on one particular flavor of chip, because the feedback we had from the product guys is they don't want to repeat the Qualcomm model where you write your software for Qualcomm and it only works on Qualcomm. And if you want to work on somebody else's chip, you've got to start again. Mm-hmm. And so we've deliberately created this framework that already works on multiple instruction sets, multiple memory architectures. We can use AI accelerators to remove that pain point.
Awesome. So if I want to make a new model of the headphone I'm making, then I can off the shelf get one of those and use your software. How does that work? Do I have to get in contact with you to get the software? How does it work? Because we're also talking about closed source and open source, and how does it work in this particular case?
Yeah, so the general process is we will give you a development kit, which has some development boards inside it. It's typically some kind of connectivity board, like a Bluetooth radio. There's a processor, which is the host. And then there's a bunch of peripheral components, depending on what your project needs. So we'll have an audio interface. You might have some sensor interfaces and so on. And then we give you access to the OS libraries and all the code. And we give you some example plugins, and then off you go.
Sounds wonderful. That's great. So that's the stage you're at. You can actually, yeah, you can basically send things to people, and people can develop on it. Do you have any products already out there with your technology, like in the market?
The first headphones are going to be launched probably in Q1 or Q2 next year. First end products with headphone manufacturers.
Can you disclose who or not?
Not yet.
Cool.
Maybe at CES they'll be announcing them.
Cool. Okay, so then Adrian, you've used this platform for your, have you? I don't know.
Yes.
And still, can you please like maybe get a little more into detail how that worked for you and what was the experience?
Yeah.
Especially versus all the other alternatives,
yeah.
if you used also other alternatives.
So while this might sound weird, I think any developer will latch onto this idea. One of the really big benefits that an operating system, or I think from this context, I rather want to describe it as a framework, that the framework like that delivers is being opinionated. So when you write a driver, you can't just go ahead and write a driver on the hardware just any way you want. There's an example of this is what a driver looks like. So there's a standard, and that, I mean, I think most developers will understand that kind of separation of concern that's already been done for you. I mean, as a developer, a lot of our work is really figuring out what something should look like. It's not building that thing. You have to figure out how should it be built? Where are the lines that separate different components from each other? And those decisions on separation of concern and where are the interfaces, those are, those can be really hard decisions to make if you're working from scratch. So these decisions have been made beforehand, and they're well documented, and you just have to fit into that framework. And then I think the second big thing is that this burden of having to deal with the plethora of divergent platforms out there, or chipsets out there, and all of their various co-processors and things is divided between you as the developer of a plugin and Gary and them who write the operating system, and then the whole community of other plugin developers. So it's just, it's this whole sort of network effect that I think, well, partly network effect, and then partly the whole thing that there's an operating system that, also tries its best to support all of these chipsets and all of these different platforms. So there's a lot of work that you won't have to do. And that, I mean, just in terms of physical work, I mean, it turned months into weeks for us. That's really the difference.
Actually, you just touched upon an interesting topic as well, which is community. Like, that's been one of my main concerns when I develop something. It's like, can I actually go to Google and search something? Or is this a completely closed environment and I have to depend on this third party all the time and they only answer whenever they want to? Are you focusing on that as well, Gary, or Adrian, if you know something about it? Is it like a community focus?
Yeah, that was really one of the founding principles of building this. The whole concept around no single one person is as smart as everybody. We want everybody to contribute to this. And the more people that we enable, as you know, the guys have already explained, it creates even further innovation. So you get that second and third tier effect where we create something and it goes off in a completely new direction that we hadn't envisaged. We can't invent everything as one group. So we're opening it up to everybody else and letting you guys be creative with it and take it where you need it to go.
So is there like a link that I can find the community on, or maybe you can share it later, or I can share it with people if they're interested in looking? Is there like a forum or something? Or...
Yeah, there's nothing official at the moment. You know, we're still in the early days of creating that, and we would like other people to create these, you know, these communities. Okay. You know, maybe the Danish Sound Cluster has their own group of people that are working in this ecosystem, and they can then build on top of that, and that becomes his own little product space.
Cool.
So maybe I can bring a perspective, Pedro.
Yes, do it.
Because it kind of also talks or harks back to the previous question, you know, about how does this look from a developer point of view? How does it work?
Yes.
And so one of the, I mean, if I just step back a bit, one of the things that we sort of do as a rule, as a company that wants to stay and survive, is to break things fast. If this isn't going to work, we need to break it as soon as possible. And so we, if you like, took it upon ourselves to prove the entire end-to-end system. That means consumer wants to buy something, goes to an app store to get it, gets it successfully, hits it, the go button, and here's something cool in the ear. Nothing less would suffice. Because if that can't work, then there's no point, or at least we're taking too big a risk. And I'm speaking as a CEO. So we did some smoke tests, and we're actually doing this, and we have done all of those components. So we have done an app store at Scotia, but guess what? It's not really an app store. It's actually the infrastructure that we use to run our business anyway. Because internally we want to share widgets and share code and make it easy to give stuff to customers. So we had that. It's just, some work on Amazon and Google and web pages and dashboards and a few themes, and that's great. So there's your app store. So we did that. But most importantly, in doing that, we said about writing the sets of APIs that would make that buildable by anybody. Because not everybody's going to want to use our app store. They want to build their own. Fine. Here's an API that you can use, that you can do the app store front end piece, but we'll store your app, your DSP IP assets, because we know about that. And when it comes to shooting it down to the earbud, you're going to need some expertise on that. It's not about putting a nice logo on a product page. So moving on to the phone. So we have this companion app, and this is something that that is in Sonical's domain, but again, maybe something that could be white labeled or taken up by a brand. And this is the companion app where you actually see the app store, and again through pure APIs. So you see the app store, you see, oh, great, I can buy an EQ from iDone. Brilliant, I love that. Oh, great, I can buy an AAD thing from Scotia. Don't know what that is, I'll try that out. Hit the buy button, and bang, it goes down onto the phone, or excuse me, onto the device. And again, we've proven, that, and, our end goal is to, obviously run an AAD decoder on a Cosmos device. And until we do that, we haven't proven the end-to-end. We haven't, if you like, played the role of the customer. But we have done all of those pieces individually and shown how, yes, you can run DSP on Cosmos. Yes, you can get like a binary of some cloud URL and present it in a gallery style to an app store front end, and then hit a Cosmos API to shoot it down to the phone, or excuse me, shoot it down to the earbud. So, yeah, so what am I saying? All those components have been proven.
Yes.
Albeit in, if you like, like hello world type contexts. But all you need to fill the rest of it is the innovation. And again, we're back to community. Who's going to make these plugins, and what are they going to do? Well, obviously, Scotia has a view on that, but now so can any company.
Awesome. I mean, you're also like challenging so I want to challenge you guys also to imagine, because you keep on mentioning the phone also as like okay, I'm going to try this app or that app. But can you guys imagine that this could go into a completely no phone scenario where would it be like a voice assistant kind of thing where you say, I want to try spatial audio, and then the voice assistant goes like, you have these 3 options, blah, blah, blah. Would you like to install one of them based on the reviews or something? I don't know. But what do you guys think about that? Can you even imagine something like that happening?
Could I have a stab at that? Neil, I think we've seen a few first stabs at voice interfaces, and I think we can all agree they're a bit awkward, right?
They are.
I mean, you know, Alexa and Siri are both. I don't know. Is there anyone who uses Siri on a day-to-day basis, or is there anyone who hasn't? Is there anyone who hasn't screamed at the Alexa yet? You know, it's a really frustrating experience, right? So, and I think it's one of these cases where we're really doing something very new, and we're trying to apply these old thinking or old paradigms to it. But at the same time, there's this other thing happening on the side, which is basically this, you know, the dawn of proper general AI. I'm specifically thinking of the GPT-3 engine, which, frankly, every time. Say again.
Can you explain a little bit what that
is? Yeah. GPT-3 is the engine developed by OpenAI, which I mean, Elon Musk is still famously scared of AI, and that's why he started a company called OpenAI. And I think people generally misunderstand. Well, maybe I misunderstand why he's scared of AI, but I don't think it's this what everyone thinks, that our you know, computer overlords will eventually dominate us and oppress us. It's more like AI is such a differentiating superpower. You know, if you develop expertise in it, that it suddenly creates this chasm between the haves and the have-nots in terms of, you know, big corporations. So, and to do proper R&D on AI is really expensive, because I mean, really big general AI engines don't run on a computer in your server room. It runs on multiples of data centers. So you need big money to experiment with that. And that's why he started OpenAI. And the result of OpenAI is this engine called GPT-3. Now, GPT-3 has resulted in a few interesting products. The one is all over social media. This one called DALL-E, which is an AI that you ask to paint you a picture of something. So paint me a picture of a teddy bear in space in the style of Salvador Dali. And this AI just does it, and does it amazingly well. One of the other more commercial outputs of GPT-3 engine, or implementations of the GPT-3 engine, is GitHub Copilot, which I don't know how many of you are playing with Copilot. It is frankly scary.
Not at all. Okay. In what way?
It is amazing. It basically you can configure it to get access to various, you know, how much it gets access to, and the most sensible thing to do is to give it access to your own code base, so that it can learn what does your software look like. And then you can configure it to keep that private, you know, or you can say, you know, I want to do the nice thing and let that add to learnings that contribute to the rest of community. But the bottom line is this AI will start, eventually it gets to the point where you write a comment where you describe in English, what do you want to do? And it will write you an entire function in C or whatever you're coding in that says, this is what it thinks you might want to write. And the level to which the sophistication that it comes up with is actually quite surprising. I mean, I'm not going to try and sell it. Just go out and try it. GitHub Copilot, you can sign up for a free trial, and it is quite amazing.
But I mean, we started in the the voice assistant, and I'm just trying to, like, okay, the voice assistant is what we have right now for audio interface.
So what I'm saying is, I don't think a voice interface will work until it's backed by a fair amount of strong AI. AI that really understands language. The thing is, it's not for, I don't think there's a solution in these very literal kind of command driven, you know, I say something, I rely on some engine really understanding what I said out of context and just triggering some command on a computer. That's not what this is going to be.
So you go like the horror movie where it's almost like a person and it's literally understanding you in a very deep level.
I think there needs to be a comprehension layer, but I think that comprehension layer sounded, even 2 years ago, it sounded quite far off, to the point where I thought voice interfaces might be dead for a pretty long time. And what's happened in the last 2 years has completely blown me over. So I think we're much closer to something like that than we know. Well, I mean, I think I'm underestimating, right? Most people on this call probably know this, right?
But I guess in the eyes of, like, for example, Gary is doing the architecture, would this be then like a specific application that someone else would develop in your platform, or how do you see that? If we wanted to go completely only headphones, would that be more like an application use of it? Or would
this will definitely have to be a cloud-backed kind of application, yeah. But I can totally see this as in Gary's ecosystem being a plugin that just happens to be cloud-backed, but it's just something that the application layer can, you know, put in the graph at the right place, and you know, and Bob's your uncle.
And hopefully it works.
Yeah, that always helps if it works.
Yeah.
I think we've had, you know, a poor experience of voice as an interface related to headphones. And I think the first product I worked on with that was back in sort of 2004 or 2005. And it was really just to replace buttons because the devices are so small and fiddly. Oh, let's replace the button to turn the volume up and say volume up. And I think since 2004, I haven't seen a single person ever do that. But, you know, lots of companies then decided, oh, well, now we need to skip the track and turn on the light. And we're trying to replace buttons with the voice. The buttons work fine and the phone works fine. So let's just keep using that. We should use our voice to do something a lot more interesting. And again, that's where some of the plugin companies that we're working with are doing astonishing things with your voice. Not necessarily about using it as an interface, although we'll get there, but understanding some of the analytics and the biomarkers and other things that your voice tells you about yourself. So it kind of comes back to this listening thing that I mentioned at the beginning. It's not just about listening to sound, it's about listening to the world and listening to your body. And if we can do that and we enable people to be creative, the headphone's going to be completely transformed.
Great. Thanks a lot, guys. We're running out of time, so do you have any last words you want to say? Then please do. Otherwise, I'll just conclude this session. I guess silence answers it. So, yeah, thanks a lot. This has been very, very interesting. I will share your contacts with people, and this will be online, so people can watch it again whenever they like. And there will be a survey at the end that people can just answer. It takes 1 minute when you switch off. So please answer it because it helps us a lot. And I think that's it. Thanks a lot, guys. It's been a wonderful experience. Bye.
Thank you, Pedro. Thank you, everybody.
Thank you.